2D changes of state. 216 temperature and changes of state. If you drop several ice cubes onto a hot frying pan, the spitting, popping cubes will dance about the pan as they melt into water, a liquid, and then sizzle into steam, a gas. The water changes physical states, but remains the same substance. When matter changes from one state to another, we call this result a phase change or change of state. Ice, liquid water, and steam are all composed of water molecules. What happened as the ice melted into liquid water and the water boiled into steam? As a substance changes state, something happens to the position and movement of its particles. The faster the particles move or vibrate, the higher the temperature. You can also say that the higher the temperature, the faster the material's particles are moving. Since the speed of particle motion and their distance apart determine the state of a substance, temperature is an important factor in the state of a material. For the remainder of this section, let's assume that, except for temperature, air pressure and other conditions that can affect states of matter are constant. The temperature of a substance is an indicator, but not a direct measure of the thermal energy present in the substance. Thermal energy is related to the microscopic random vibrations and motions of the particles of matter. For a given object, the greater the amount of thermal energy it contains, the hotter it is. Thermal energy flows into an object by heating it. A loss of thermal energy results in cooling. 2.17 Melting and freezing. Melting. As a solid, pure substance, an element or compound gains thermal energy, its temperature increases. If the solid absorbs enough thermal energy, its particles vibrate so rapidly that the attractions between particles can't hold them in fixed locations any longer. They break free and begin moving around in the liquid state. We call this physical change melting. The temperature at which a pure solid turns into its liquid phase is its melting point. The melting point of pure ice, for example, is 0 degrees Celsius, 32 degrees Celsius. Every pure solid has a distinct melting point. This is just one of many physical properties that can help identify pure substances. Solid mixtures can melt too. However, the melting point for a mixture of substances isn't a unique temperature. This is because a mixture's melting point depends on the proportions of the materials in the mixture. The ratios can differ from one mixture to the next, and so does the melting point. For example, un metal mixture, an alloy contains only gold and silver. The alloy will melt at different temperatures depending on the percentages of gold and silver. See Figure 2 to 27. Freezing. When a liquid cools, its particles slow down. Eventually, the motion is slow enough that the attraction between the particles can hold them in fixed locations. As particles clump together, they enter the solid state. When all the particles in the liquid are trapped and can no longer move about, the change to a solid is complete. We call this process freezing. This occurs for pure substances at a uni-temperature called the freezing point. The freezing and melting points for any pure substance are the same temperature under the same conditions. The freezing point of a mixture depends on the ratios of the different substances in the mixture. The ratio of the parts in the liquid mixture changes as freezing takes place because the different parts usually have different freezing points. The substances with the highest freezing points freeze first as the mixture cools, increasing the ratio of the others in the remaining liquid phase. 2.18 Vaporization and Condensation. The particle model and vaporization. Vaporization is any process resulting in a solid or liquid substance changing directly to a gas. Let's look at water to see what's happening. Molecules in liquid water are moving constantly in random motion. Collisions with other molecules jostle them. They roll, side around each other, and vibrate. Most molecules move at a moderate speed. In some collisions, a molecule's motion may slow when another molecule strikes it, or it may pick up speed. A few molecules are moving faster than the average speed of the others. When one of these collides with another fast-moving molecule, the second may gain a lot of extra speed. If this molecule is near the surface of the liquid, it may be able to escape the attractions of the other molecules in the liquid and fly free. The molecule then enters the gaseous phase above the liquid. temperature, pressure, and vaporization. The rate of vaporization refers to how fast liquid water changes to a gas. It depends on two factors: the temperature of the water and the pressure the water's vapor exerts on its liquid or solid phase. Let's look at the liquid to vapor phase change to understand what happens. As the water's temperature rises, molecules in the water are moving faster, so it's easier for them to gain enough speed to escape the liquid phase. Warmer water causes more molecules to leave the liquid phase, increasing the vaporization rate. As a liquid cools, the opposite happens and vaporization slows down. At the surface of any liquid, molecules in the liquid and vapor phases continually exchange places. Some of the vapor molecules near the water's surface slow down enough to be captured by the liquid phase. Other molecules from the liquid enter the vapor phase. For liquid water open to the atmosphere, more molecules are lost to the air than return. Over time, the number of water molecules in the liquid grows smaller, and the liquid water will eventually disappear. In a closed container, such as capped soft drink bottle, water molecules escaping the liquid phase collect in the vapor space above the liquid. At first, the number of molecules becoming vapor is much greater than that returning to the liquid. But as the number of water vapor molecules increases, more and more are likely to return to the liquid phase. Eventually, the number of water molecules vaporizing equals the number of water vapor molecules returning to the liquid. As long as the temperature doesn't change, this can go on indefinitely in a closed container. The amount of liquid water doesn't appear to change because both processes are occurring at equal rates. They are in equilibrium. Vapor pressure. The water's vapor molecules exert a pressure on the liquid water. This is in addition to any other gas pressure in the container. When the gas and liquid phases of any pure substance are in equilibrium, as we just described, scientists call the pressure that the gaseous phase exerts vapor pressure. Vapor pressure is a property of the liquid substance and is directly related to temperature. The higher the temperature of the liquid is, the higher its vapor pressure. For two substances under the same conditions, the one with a higher vapor pressure will vaporize faster. For example, rubbing alcohol has a higher vapor pressure than water, so it evaporates off your skin faster. A pure substance's equilibrium vapor pressure, measured at standard conditions, is an identifying property of the substance. Kinds of vaporization. Boiling is the fastest kind of liquid vaporization. The liquid's temperature is high enough that vapor bubbles form inside the liquid and rise to the surface. Bubbles appear wherever the liquid's vapor pressure becomes greater than the surrounding liquid pressure. Air pressure above a boiling liquid doesn't affect the vaporization rate. It only determines at what temperature bubbles can form. The temperature at which boiling begins is the boiling point of the liquid. Vapor bubbles can form anywhere in the liquid where the temperature is at the boiling point. In a pot of water on the stove, the hottest point is nearest the heating source. So bubbles form in the bottom layer of water, since that reaches the boiling point first. As the hot water circulates in the pot, the whole mass reaches the boiling point. Hot water vapor bubbles, steam, form nearly everywhere in the liquid, rise to the surface, and burst. The boiling point of a pure substance is a unique property of that substance. Since atmospheric pressure affects its boiling point, scientists must measure this temperature at standard conditions so that they can compare it to other substances' boiling points. For example, the boiling point of pure water is 100 degrees C, 212 degrees C, at normal atmospheric pressure. The boiling point of rubbing alcohol is only 82.5 degrees C, 181 degrees C, at the same pressure. Evaporation is the kind of vaporization that happens when a liquid's temperature is anywhere between its melting and boiling points. Unlike boiling, evaporation can occur only at the surface of a liquid. We described the process of evaporation in open container vaporization earlier in this section. The rate of evaporation of a liquid in an open container depends not only on the liquid's temperature, but also on the surface area of the liquid, that is, evaporate. Ing. A liter of water in a wide pan will evaporate much faster than a liter of water in an open soft drink bottle at the same temperature. Sublimation happens when certain kinds of solids seem to evaporate. The solid's molecules enter the vapor state without becoming a liquid first. Sublimation occurs at temperatures below the solid's melting point. Solids that sublimate into a vapor appear to gradually shrink over time and disappear. Ice cubes shrinking in your freezer is probably the most common example of sublimation. Mothballs used to protect clothing against moth larva damage also sublimate and disappear over time. Just as with evaporation, sublimation occurs only at the surface of a solid. Condensation and deposition. Freezing is the opposite of melting, and condensation is the opposite of vaporization. Condensation occurs when a vapor cools and changes to the liquid state. Vapor temperature and pressure determine when condensation occurs. Dew is a good example of condensation. In the cool of the evening, water vapor molecules slow down when they collide with slower-moving air molecules in the cool atmosphere. As the water vapor temperature drops, the molecules move more and more slowly. Eventually, their attraction for each other causes them to clump together, forming microscopic water droplets. The exchange of water molecules between these droplets and the air still occurs, but at a lower rate than the clumping, so the droplets grow larger. These microscopic droplets come together and form visible drops of dew on cool surfaces, such as blades of grass, spider webs, and car windshields. Drops of water on cold beverage glasses result when the water vapor molecules slow as they collide with the cold glass surface. The opposite process to sublimation is deposition. Solids that sublimate to a vapor also readily deposit as a solid under certain conditions. Deposition occurs when the rate of vapor molecules returning to the solid exceeds the number of molecules sublimating away. Perhaps you have noticed the feathery crystals of ice that form on packages stored in a freezer, especially if you live in a humid locality. These ice crystals build up due to the relatively large amount of water vapor in the air contacting a surface that is below the freezing point of the vapor's liquid state. This is also the reason frost appears on outside objects in chilly weather.